with liver and muscle, you will have more of glycogen in the muscle because there are more muscles than your liver. Okay? So there's a table for that, and you'll be able to see it. Glycogen is synthesized from glucose. We will go into that. Glycogen degradation produces glucose 1-phosphate as the major product, but a few free glucose is also formed. Now that glucose 1-phosphate will be acted upon by a mutase. That phosphate will be transferred to carbon 6 and it will be glucose 6-phosphate. And then the phosphatase comes in, removes that phosphate, then you have free glucose. Now, glucose units are removed with the non-reducing ends of glycogen by an enzyme known as phosphorylase, which produces glucose 1-phosphate. Okay. 3 of the 4 glucose units at the branch point are moved by a transferase to the non-reducing end of another chain. The remaining glucose unit that is linked at alpha 1,6 at the branch point is released as free glucose by an alpha 1,6 glucosidase. Okay. Liver glycogen is used to maintain blood glucose during fasting or exercise. Its breakdown is stimulated by glucagon or by epinephrine. Now you must have already an idea of what epinephrine is, no? Or adrenaline. There is what we call as adrenaline rush. What do you mean by that? There is a source of adrenaline in your blood. That's what we call adrenaline rush. So we will talk about that epinephrine and glucagon also. Muscle glycogen is utilized to generate ATP for muscle contraction. Epinephrine stimulates muscle glycogen breakdown. So remember, epinephrine stimulates muscle glycogen breakdown. Another name for epinephrine is fight or flight hormone. So you and me are confronted with whatever it is. Your life is in danger. It's either you face your tormentor to fight or to run away. So that's flight. So that's why it's called fight or flight. A hormone. And remember this, it is the liver glycogen that gives glucose to the blood in order that the blood increases its glucose content when you are in fasting. The muscle glycogen is being broken down not to augment or to increase the blood glucose, but the muscle degradation of glycogen is only for the muscle itself. Okay? So you have 2 organs there. Liver, which gives its glucose to the blood so that all the other tissues can be having glucose, but the muscle keeps the breakdown of glycogen to glucose for itself. So you have two kinds there. A liver which is generous with their natural resources, while the muscle is very selfish for what it has. No? Okay. So increases liver glycogen, muscle glycogen, never mind the extracellular glucose. Liver glycogen percentage of tissue weight is 5. Okay, it's 5. It's very high compared to muscle glycogen, which is only 0.7% by weight. But because the liver is only 1.8 kilograms and the muscle is 35 kilograms, okay, you will only have 90 grams from the liver, while you will have 245 grams from the muscle. Can you see that big difference? Now, of course, you look at the tissue weight. The tissue weight of liver is 1.8 kilograms, while the muscle is 35 kilograms. No tissues. Okay. So it says here, liver glycogen functions as a reserve to maintain blood glucose, while muscle glycogen is within the muscle itself, because the muscle does not have a phosphatase which removes the phosphate from glucose. So that glucose can never be free and cannot get out of the muscle cells. While the liver has a phosphatase and removes the phosphate from glucose, and you have now what we call a free glucose. When we say free glucose, it means without the phosphate, nothing is attached to it. It's free. Okay? It has. Now, if you have some in the degradation of your enzymes, the enzyme for degradation of glycogen, you if some enzymes are deficient or absent, you will have what we call glycogen storage diseases. Huh? Okay, let's talk about that later. Glycogenesis occurs mainly in the muscle and the liver. Glycogen biosynthesis involves UDP glucose. So now glucose is attached to a nucleotide. UDP is a nucleotide. Uridine diphosphate. Uridine there, U is from uracil, base, in nitrogenous base, and then you have two phosphates attached to it. And that UDP attaches itself to glucose. So that would be the start of glycogenesis. Okay? So let's just look at right away this one. How do we remove this? Remove na siya. Really? I think this is smaller. Dili, kinik figure ano na tagamay. Oh, ito na to. Okay. So we have here, starting from glucose, which enters the cell because this is free glucose. And then it is phosphorylated by glucokinase. So this is a liver cell, glucokinase, and becomes glucose 6-phosphate. It is converted to glucose 1-phosphate by a mutase, phosphoglucomutase. There you are. And then that glucose 1-phosphate is acted upon by this UTP, uridine triphosphate, a nucleotide catalyzed by UDP glucose pyrophosphorylase. And you have now UDP glucose. Okay? Now, UDP glucose interact with glycogenin. Glycogenin is a protein in which the glucose units are attached to it to become a glycogen tree. No? Tree, kahoy. Because this formation of glycogen is resembles a tree with branches. No? Okay, so glycogenin is that part of the liver cell in which glucose units are attached to each other to form a glycogen tree. Now, during glycogenolysis, or the breakdown of glycogen, this glycogenin, there are a few glucose units attached to it and can never be removed by glycogenolysis. So they always have glucose units. Now this is because when the glycogen that is attached to glycogenin are being chopped, there are always a few glucose units still attached to it and cannot be removed. So that when things is favorable, where there's plenty of glucose, then those glucose units can be attached to the glycogenin with some glucose units already. Do you get it? All right. So UDP glucose attached to your glycogenin, catalyzed by what we call glycogen synthase. All right. That glycogen synthase now will have several glucose units added to it now in a 1,4 linkage. 1,4 linkage. So several glucose units will be attached until you have one straight chain, and then a branch will be formed. A branch is created by a linkage known as alpha 1,6. Now remember, when we say 1, that is carbon 1 of 1 amino acid, fatty acid, glucose, I'm sorry. Carbon 1 of 1 glucose units attached to the other glucose units at carbon 4. So that's why you will have alpha 1,4 glycosidic linkage. Glycosidic linkage. Okay? So that's why you have here a branching enzyme. And now you will have a proliferation of those glucose units that will be attached in a 1,4 and a 1,6 linkage. When we say 1,6 linkage, it is a branch. Okay? All right. So let's try to see another illustration. Oh, I'm sorry. Oh, this is what we call UDP glucose. This is your glucose. This is your nucleotide, uracil, ribose, and phosphate. Now those P there. Now you have a glucose there attached to your uridine nucleotide. Okay? That is UDP glucose. All right, here we are. Okay? One glucose unit. No. Another glucose units, 1,4, 1,4, 1,4, 1,4. Now here is a branch. That's 1,6. After 1,6, you have 1,4, 1,4, 1,4. Okay. This is your glycogenin attached to a protein known as glycogenin, and you have these several glucose units. This cannot be attached or detached during breakdown. So you have an incoming glucose through your glycogen synthase. Oh, those are the incoming glucose. This one there, colored blue. Or what's this? Colored blue-green. Oh, okay. So it is attached. 1,4, 1,4, 1,4, 1,4, 1,4, 1,4. All right. Once you have glucose units, okay, from a branch about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Once you have 11 glucose units or glucose residue from a branch point here, then an enzyme takes 6 glucose units starting from here. This is the reducing end. When you say reducing end of your glucose, that is where your C double bond O. That is your C double bond O or your aldehyde. Okay? So you take 1, 2, 3, 4, 5, 6. The branching enzyme cuts this off and transfer it to another segment. So here, there you are, is there, and creates a 1,4 linkage, a 1,6 linkage. This is 1,6 linkage. So that's why it's called a branch. Now, this is free to receive glucose unit so that it will also goes. This one can have another glucose unit, or this one can have glucose units. But always remember, every time you will have 11 glucose units. When you have 11 glucose units, the branching on enzymes will always take 6 units and transfer it to form another 1,6 linkage, a branch. So, if you look at this is in combination of glycogen synthesis. Glycogen synthesis is just one straight like that. One chain. While a branching enzyme cuts off 6 and transfer it. So you can have as many later on branches. You can put a branch here, or this one will now lengthen. You can put a branch there, and so on. And so you will have something like that. This is the reducing end, so meaning to say we start from here. This black thing here, this black, these are 1,6 linkages. Now this one is just a straight 1,4, 1,4, 1,4, 1,4. This one is 1,4, 1,4, 1,4, 1,4 linkage. This one is 1,4, 1,4, 1,4. Did you get it? So you start from there. Now imagine that there is that protein there, glycogenin. So this is, it looks like now a tree. There is a term before which was used, but it is now not being used. It goes like this: arborization of the glycogen. Okay, then you will ask, what is arborization? All right, arbor means tree. When I was in our high school, elementary and high school, that was long time ago, no? But not as long as Magellan's time. We used to have, or you ask your mother or your parents, have they experienced this? That we celebrate a day for the tree. And we call it Arbor Day. Arbor Day. And what do we do in Arbor Day? We plant trees. We plant trees. So we are told to bring at least 3 fruit trees, because during when we first meet, whether you are in grade school or high school, our teacher will always say, you have now to have a seed of a tree, of a plant or a fruit tree, like nangka, avocado, or whatever. And then you will have to put it in a can with soil so that it will grow, it will germinate. So that by the time we will have arbor tree, we already have seedlings. And we carry three seedlings. No? We bring along three seedlings, we go to the mountains. It's just like a picnic because we have to bring our own food and water. And of course, something to dig the ground. And we usually have a bolo. We go there, then we plant trees. We plant the trees. That is Arbor Day. Now, I do not know what happens to our educational system that they remove that. They remove that important activity for children in order just to give at least a connection to the trees. As you have now learned that you are connected to the trees because the tree gives off oxygen for you to inhale, to keep you alive. And in return, you give off carbon dioxide so that the tree will inhale it and form starches so that you can eat from the tree. No? I don't know why they did that. They stopped that. So there is no love for the tree or plants that matter. Okay, so going back to this, then you have all of this now proliferating, and we have this now what called arborization of the glycogen tree because there is now branching, and the leaves are there. No? So it looks like a tree. If you let this stand, this is the stump, this is here, and then you let it stand, it looks like a tree. So that's why older textbooks mention arborization of glycogen. All right, we have decreased so much from that, no? Okay. So again, going back to this. So what do we start? Glycogen, a 37 kilodalton protein that is glucosylated. Yan mo na? A glucose on a specific tyrosine residue of the protein because tyrosine has an OH. And you have OH also with your glucose, and you remove a molecule of water, so you create a linkage. Tyrosine residue by UDP glucose. Glycogen catalyzes the transfer of further 7 glucose residues from UDP glucose in a 1,4 linkage to form what we call a glycogen primer. So, to the glycogen primer, we put more UDP glucose until you arborize the glycogen. Create 1,6 linkage as a branch, and then you continue creating alpha 1,4 linkages. Okay. The glycogen remains at the core of the glycogen granule. Glycogen synthesis catalyzes the formation of glycosidic bond between carbon 1 of the glucose of UDP glucose and the carbon 4, the terminal glucose residue of your glycogen, liberating UDP. The addition of a glucose residue to the pre-existing glycogen primer occurs at the non-reducing end. Okay. All right. There you are. Oh. Okay. So if you see this 1,4 linkage, and if you have a cross there, that is 1,6 linkage. This colored glucose is labeled glucose residue. Label glucose residue. Meaning when they were doing some research on this, they have to label the glucose residue. Because you cannot see it. You cannot see the glucose molecules. But you can only detect it. So they label this with usual label, tritiated hydrogen. The usual label is tritiated. I was asking my apo here if he knows about tritiated hydrogen. That is one of the label element which can be detected. Okay. So this is the one. So the two enzymes, glycogen synthase and branching enzymes, come into play so that your glycogen becomes arborized. So this is the beginning already. You look at this. So if you have branches and all of that, then you have a glycogen tree. Branching involves detachment of existing glycogen chain. So branching enzyme transfers a part of 1,4 chain, alpha 1,4 chain, 6 glucose units, look at that, to a neighboring chain, to form an alpha 1,6 linkage, establishing a branch point. The branches grow by further additions of 1,4 glucosyl units and further branching. So you see how nice is your body? Oh, there you are. That's your branching. Oh. How? So what we have built, we'll try to break it down. No? It's always like that. Build up, break down, build up, break down. You should always remember that nothing in your body is permanent. There is always a turnover. The turnover might be in a few hours or few minutes, or it may take weeks or months a turnover. Meaning to say, your cells are destroyed and replaced. The skin that you carry now is not the same skin when you were a baby, because those skin have been shed off. The bones that when you were a baby are no longer there. They are replaced several times already. So there's nothing permanent. And you can just look at your hair. Everyone is growing long hair now, no? Because of this pandemic, we are afraid to go to the barber shop to have our hair cut. So just look at that, your hair comes longer and longer and longer. And you just have to cut it. Your nails are growing. So is your skin, pushing out the epidermis, because there will be a new epidermis. So the one on top will just shed off. Okay. Every time you take a bath, when you rub your towel, skin cells are removed. The epidermis. See? Okay, glycogenolysis is not the reversal of glycogenesis, but it is a separate pathway. It is a separate pathway. Okay, let's go back again. Here we are. This is the pathway for glycogenesis. There. So you have now glycogen on top. And when we go this way, we are breaking it down back to glucose 1-phosphate and then to glucose 6-phosphate. And then removal of the phosphate by a phosphatase, it becomes now free glucose. Okay. Now looking at this, glucose goes this way to become glycogen, and glycogen being broken down back to glucose again. It seems like a useless cycle, di ba? If there is no control to this, it becomes a useless cycle. Okay. When did we say that you will have to store glycogen? When you have plenty of glucose. When all your needs for fuel are already being met, then you start storing the glucose in form of glycogen. And if that continues, okay. So if there is a continuous supply of glucose, it will always stored as glycogen. It will stay there. And it is just only broken when there is a need to increase the amount of glucose in the blood. Okay? All right. So as I've said, from glucose to glycogen, then glycogen back to glucose. Looks like a useless cycle. However, this is being controlled. And we control these two enzymes. Glycogen synthesis for glycogenesis and glycogen phosphorylase for glycogenolysis. So how does this control work? The control is done by phosphorylation. So what do you mean by that? Phosphate is added. And the other one is dephosphorylation, meaning removal of the phosphate. Okay. Now, glycogen synthase is active when it does not have a phosphate. No phosphate. So this is active. Okay. Your glycogen phosphorylase becomes activated when you add a phosphate. So they are opposite. Glycogen synthase active without a phosphate. Glycogen phosphorylase active with a phosphate. See? All right. So when does this phosphorylation and dephosphorylation come around? Okay. Let's look at this breakdown first. You will know. Huh? Look at this, the breakdown. And we said we have to phosphorylate this so that glycogen can be broken down. Without this being active, the glycogen is just stored. Okay. If you look at this cyclic AMP, it affects this one, it affects this one at the same time. Cyclic AMP has a negative effect on glycogen. Cyclic AMP has, no, it has a positive effect. So this is activated. That's positive. No, that is negative. Cyclic AMP. When is cyclic AMP formed? So when is this formed? You look at this. Positive effect on cyclic AMP. And what are they? Glucagon and epinephrine. What did we say about cyclic AMP? We said it is a hunger signal. Oh, hunger signal. So it means you are not eating. And what happens when you are not eating? Okay. No glucose coming from absorption of glucose from the intestinal tract because there's nothing in it. Diba? So, what happens to the blood glucose? It goes down. And when the blood glucose goes down, it inhibits the release of insulin, but it stimulates the release of glucagon. Okay? And then glucagon induces the formation of cyclic AMP through the activation of an enzyme known as adenyl cyclase. Adenyl cyclase converts ATP to cyclic AMP. Oh, there you are now. You have the hunger signal, cyclic AMP. Oh, and then what happens if you have cyclic AMP? The cyclic AMP in turn activates another enzyme, protein kinase. This protein kinase has two targets, glycogen synthase and glycogen phosphorylase. And what did we say about kinase? It adds a phosphate. So it adds a phosphate to glycogen synthase. It adds a phosphate to glycogen phosphorylase. What happens when glycogen synthase has a phosphate? It is inhibited. But a phosphate on glycogen phosphorylase is very happy. Is stimulated. So you stop the formation of glycogen, but you start the breakdown of glycogen. So that whatever glucose 1-phosphate that will be formed, it will not be taken up by the glycogen synthase to form glycogen because it is inhibited. Yeah? So this is an inhibition and stimulation or a control by just using a phosphate. One stone hitting two birds. One bird, glycogen synthase, the other bird, glycogen phosphorylase. And glycogen synthase, when it has a phosphate, is inhibited. The glycogen phosphorylase, when it has a phosphate, becomes activated. So it starts breaking down glycogen to glucose 1-phosphate. Glucose 1-phosphate becomes glucose 6-phosphate. The glucose 6-phosphate now is acted upon by a phosphatase, removal of the phosphate, and you have now a free glucose. And this free glucose goes into the bloodstream. You see? All right. But that is not the end of the story yet. So let's look at this. So glycogen phosphorylase is active. It breaks one glucose unit starting from the reducing end, one glucose units at a time until it reaches. Now, let's look at this. All right, there you are. So, look at this, phosphorylase. So what does it do? Removes glucose units here, glucose units there. No, release it as glucose 1-phosphate. Now, when you have 1, 2, 3, 4 glucose units left from a branch point, another enzyme comes around and removes the 3 units and transfer it here to adjacent chain. That's what happens. No? So what is left? Only one glucose, alpha 1,6. Then a debranching enzyme comes around and cuts this off. And this is 1,6 linkage man. Kani siya 1,4 man eh, 1,4, 1,4. Only at the branch point you have a 1,6. So it requires another enzyme, a debranching enzyme. And that is cut off. And the good thing about this is that it is released as a free glucose. Released as a free glucose. Okay. It is not glucose 1-phosphate, but free glucose. So this goes to your bloodstream. And so you have your phosphorylase now acting on this, and so on. Until you have a branch point again. No? So yeah, look, there is none, so this just can go on. Okay? So let's go back to this one. There. So you see, you have your glucan transferase, you have your debranching enzyme, and what is removed? Free glucose from the debranching enzyme. Okay? Then the rest are glucose 1-phosphate converted to glucose 6-phosphate. Some of that becomes free glucose, or it goes to glycolysis and pentose phosphate pathway, another pathway. See? Now, when you are now eating back, there's plenty of glucose, this pathway now will go this way. So how is this brought about? This one is phosphorylated. Look at this. When your blood has a high concentration of glucose, insulin is released. This one is no longer released, glucagon. So what happens now? Insulin inhibits, look at that, negative, cyclic AMP. So cyclic AMP cannot activate your protein kinase that adds a phosphate there and adds a phosphate there. Okay. Then a phosphatase cuts off the phosphate here and the phosphate here. So both have no phosphates. And glycogen synthesis is active without the phosphate. This one becomes inactive because this can only be activated by a phosphate. Without a phosphate, there's no more activation. So you shut this off and you continue building. because now you have plenty of glucose because you are eating back. There is no more fasting. You get the idea? Huh? So there you are, plus sign stimulation, negative sign inhibition. Insulin decreases the level of cyclic AMP after it has been released. Oh. It has been reached by glucagon or decrease the level of cyclic only after it has been raised by glucagon or epinephrine. It antagonizes their action. Glucagon acts on heart muscle but not in skeletal muscle. Remember that. What acts on the skeletal muscle is epinephrine. And it has the same effect as glucagon. So, glucagon acts on heart muscle but not in skeletal muscle. What acts on skeletal muscle is epinephrine. That's why we have here glucagon, epinephrine. Glucan transferase and debranching enzyme appears to be two separate activities of the same enzyme. Meaning to say, one enzyme with two activities. A transferase activity and a debranching activity. So, but they are not too sure about it because they use the word appear to be two separate activities. They are not sure yet. How can you be very sure when you cannot see the reaction? Okay? So there you are. Glycogenolysis. So remember this, in the liver, but not in the muscle, glucose-6-phosphatase. That is why the muscle in glycogenolysis cannot form free glucose. All right, we have here what we call glycogen storage disease. Okay, this is rare in Filipinos. In European countries, they have this, but not really very common. No, not very common, but they have. But this one is very rare in the Philippines or Filipinos, unless Filipinos marry Europeans and their offspring may have like that, glycogen storage diseases. Now, why Europeans? Because Europeans are Europeans have what we call this genetic disorders because once upon a time in the old Europeans, they practice marrying within the family. It is common to them marrying their first cousins. And they even go to extent of brothers and sisters marrying. Why? Because it was ruled by, what you call this, kingdoms. And in a kingdom, you have a king and a queen. And in order to preserve the lineage, they marry within themselves. To preserve their power and their hold in their kingdom by marrying within the family. And so what happens? The recessive gene becomes now dominant. And this is what happens. Whereas we Filipinos, we are more advanced in civilization, we do not go into these things. Diba? So there is less there is less of genetic disorders. What we have in common are infectious diseases. No? We have more in common infectious diseases caused by organisms, not by genetic disorders. Okay, so we have this. So you have here type O, absence of glycogen synthesis. So features hypoglycemia because you do not have glycogen, because you don't have this. So what happens? You do not have glycogen as a reserve whenever the blood glucose goes down. So unless the the person eats, then this can be remedied. Then we have von Gerk's disease, glucose 6 phosphatase. So if you do not have glucose 6 phosphatase and you have this glycogen synthesis, there will be an accumulation of glycogen. Because once the glucose becomes glucose 6 phosphate, it will be formed. Because no phosphatase, no removal of the phosphate, so it cannot become free glucose. So there is no breakdown of the glycogen. They always be at glucose 6 phosphate and then revert back to glucose 1 phosphate and then go back again by your glycogen synthesis forms glycogen. Okay. There's another one, endoplasmic reticular glucose 6 phosphate transporter. So there is no transporter of glucose 6 phosphate. So you will have similar glycogen accumulation. Okay. Next one is Pompe's disease. So this is in the lysosome. The lysosome is a bag of enzymes. Okay. And these lysosomes can break down alpha 1,4 and alpha 1,6 linkages. So if we do not have this, there will be an accumulation of glycogen in the lysosomes. Because the lysosomes and the lysosomal enzymes are not there. Then you have limit dextrinosis or Forbes disease or Core's disease. Is liver and muscle debranching enzyme. So the debranching enzyme. So you will have a glycogen tree in which there's a branch, even one residue of glucose there. So there are plenty of branching. And that cannot be removed because you do not have a debranching enzyme. Okay? So fasting hypoglycemia, as a result, there are plenty of glycogen, the liver enlarges. No? There's muscle weakness. Okay. Then we have limit stenosis. It is only the liver debranching enzyme. So similar to the one on top, Forbes or Core, but no muscle weakness because it does not affect the muscle. It's only the liver enzyme. Then we have Anderson's disease. What happened here is there is no branching enzyme. So you do not have arborization of the glycogen. You will have chain of glucose units, one after another, without branching. So the liver increases, accumulation of polysaccharide with or with a few. No, without or with a few branch points. Death from heart or liver failure before age 5. So they die. Huh? So those are the diseases. We do not have this. We do not have this glycogen storage disease. If there is, that's because perhaps marriages with with outsiders or with foreigners. So, ug lumad ka nga kaliwat ni Lapu-Lapu, wala ka ani. Type 4, type 5, muscle phosphorylase. Now, you cannot break down your glycogen in the muscle. That's McArdle's disease. While if it is in the liver, it's called Hare's disease. Not his, but Hare's disease. And then muscle and erythrocyte, phosphofructokinase 1, Stenosis disease. Then you have liver phosphorylase kinase is absent, hepatomegaly, hypoglycemia, and so on. Liver and muscle phosphorylase kinase, again hepatomegaly. Cyclic AMP-dependent protein kinase A, hepatomegaly again. Because you cannot break down the glycogen. The glycogen will be just accumulated in the liver. Okay? So it says that glycogen granules can also be engulfed by lysosomes, where acid maltase, hydrolysis of glycogen to glucose. This is important in glucose homeostasis in neonates, where its glycogenesis and glycogenolysis is not yet well established. Genetic lack of lysosomal acid maltase causes type 2 glycogen storage disease known as pumping. Again, lysosomes under hormonal control. And again, the hormones involved would be insulin, glucagon, epinephrine. Cyclic AMP integrates the regulation of glycogenolysis and glycogenesis. I've given you that when we were taking the illustration of glycogenesis, glycogenolysis. So this is how your cyclic AMP form. That's adenyl cyclase here, acting on ATP, and then you form this one, a ring. So that's why it's called cyclic AMP. So two phosphates are removed, as pyrophosphate or PPI, and then that forms a ring. Then so that is cyclic AMP. Cyclic AMP is destroyed by phosphodiesterase. It acts on your cyclic AMP, cuts this off so that there will be no more ring. And you only just have AMP. AMP will be formed. Phosphodiesterase is very, very, this is also an isozyme. There are 5 isozymes of this phosphodiesterases, 1, 2, 3, 4, 5. And phosphodiesterase 5 is important in the penile tissue. This is the enzyme that is inhibited by sildenafil. Now I will talk about that. This is just only to give you an idea of this one. This is an isozyme. It removes a phosphate. Destroys, not remove phosphate, but destroys your cyclic AMP. there's a cousin to cyclic AMP. And instead of A or adenine, you have guanine. And we call it cyclic GMP, which can also be deactivated by a phosphodiesterase. And it becomes just guanosine monophosphate. Okay. Okay. We have seen that already. Cyclic AMP activates glycogen phosphorylase. Now, this is control of glycogen phosphorylase in the muscle. It's very easy to follow. You can easily follow that. I already given you the idea when we have that glycogenesis, glycogenolysis, and its control. Calcium synchronizes the activation of glycogen phosphorylase with muscle contraction. So this is, if you remember your glycogen, the breakdown of glycogen in the muscle, the glucose that is formed there is glucose 1-phosphate and become, glucose 6-phosphate, and it is directly used by the muscles. And it does not give it to any other tissue but to the muscles only. Breakdown of glycogen in the muscle increases the onset of contraction. The same signal is increased by calcium concentration. It is responsible for the initiation of both contraction of the muscle and glycogenolysis, breakdown of glycogen. Naturally, because you need energy. So you have to break down the glycogen. Glycogenolysis in the liver can be cyclic AMP independent. Can be. It just, okay. In the liver, there is cyclic AMP independent activation of glycogenolysis in response to adrenergic receptors by epinephrine and norepinephrine. This involves mobilization of calcium to cytosol followed by calcium calmodulin sensitive phosphorylase kinase. Cyclic AMP independent glycogenolysis is also activated by another hormone, vasopressin, oxytocin, and angiotensin II, acting either through calcium or phospholipid phosphatidylinositol biphosphate pathway. Protein phosphatase 1 inactivates glycogen phosphorylase. Okay, so that's your phosphatase there, which removes the phosphate from the phosphorylase. So once you remove the phosphate there by a phosphatase, then that becomes inactive. activities of glycogen synthesis and phosphorylates are reciprocally regulated. I've shown you how that is related. No, I will find that. So, glycogen metabolism is regulated by a balance of glycogen synthesis and phosphorylase. Okay. So if one is active, the other is inactive. So meaning to say, when glycogenolysis is active, glycogenolysis is inhibited. When glycogenesis is active, glycogenolysis is inhibited. So glycogen storage disease are inherited. Whenever I have this, I always think of a question I have when I was still a student. Inherited. When I was still a student, we have our questions are not the way we are doing it now. Our questions before includes everything from filling the blanks, true or false, essay, and so on. Then one of the questions they have in urology says, it's a filling the blanks, and it says, blank is blank and blank. Blank is blank and blank. I really don't know what goes into the mind of our instructor before that. Can you answer a question like that? Blank is blank and blank. It reminded me because of this inherited. One of the answers is inherited. The answer is cystinuria is inherited and incurable. Can you imagine if you are being asked a question like that? So it always reminded me when I say inherited or the word incurable, that question always goes back to my head. I'm always reminded of it. Cystinuria is inherited and incurable. Blank is blank and blank. All right, that was in the past. Let's not glorify the past. Sometimes the past is depressing. So if you are living in the past, you are depressed. And if you are anxious, you are living in the future. you are at peace, there you are living at present. No? So, Marina. All right. What have we had? Citric acid cycle. Then we have, what comes after that? Glycolysis.
Glycolysis.
And then
Glycolysis
glycogenesis,
po.
glycogenolysis. And later na, pentose phosphate pathway, uronic acid pathway, and how other sugars are metabolized. Okay? We have questions from glycolysis to glycogenesis and glycogenolysis. Hi. Writing o. Okay. I know biochemistry is hard. When I was studying biochemistry before, 1, 2, 3 pages, I am asleep already. And that's why I said, if you cannot sleep, you read biochemistry. And you will sleep. Oh, do I hear any comment? No comments, no questions. Do we still meet next week? Huh?
I think, Doc, Christmas break na, Doc.
Christmas break na. Oh, Merry Christmas na din.
Merry Christmas, Doc.
Merry
Merry
Christmas.
Christmas, Doc.
Malang Pasko, Doc.
Doc, Merry Christmas po.
Doc, pinaskuhan, Doc.
Merry
Pwede.
Christmas, Doc.
Mas kami sa
Merry
inyo, Doc.
Christmas. Sige, paswab na. Magpaswab na. Ang health protocol niya, lisod ba? When you go out from your place, do you have to be swab?
Yes po, Doc.
So from one place to another, like Samar to Leyte.
Pag lalabas po, Doc, sa CPS.
So from Tacloban City, if you
Kailangan lang yung documents, Doc.
go to the towns of Leyte, do you have to be swabbed?
Yes po, Doc.
So,
Decent health certificate na, Doc.
But Ormoc is very strict. Diba? You have to have travel documents.
Yes, Doc.
Yes, Doc.
Tacloban is not so strict.
Yes, Doc. And the good news, Doc, waray liquor ban. Yan.
Okay. So we'll just stay at home. Just stay at home. Anyway, we have so many Christmases already. So let us just have this Christmas, different from the other Christmases that we have. let's just sacrifice a little. We do not die if we cannot celebrate Christmas. Okay? But Christmas can always be celebrated. You can celebrate Christmas in your heart. All right, so no questions, then we'll call it a day. Okay?
Thank you, Doc.
Thank you,
Thank you
Doc.
po.
Thank you,
Thank you
Doc.
po, Doc.
Thank you,
Love
Doc.
you.
Thank you, Doc.
Thank you, Doc.
Thank you, Doc.
Thank you, sir. Thank you.
Hmm?